Students, we will now continue our lesson to one of the component in details. Just now we have covered the waveforms. We have covered the on characteristics, the off characteristics of an ideal switch, as well as a non-ideal switch. So our focus will be on the non-ideal switch. And right now, as an example, we will go into one of the component, the metal oxide field effect transistor, or in short, we call it Mosfet. Okay, students just want to recap the purpose of these three components. They are meant to be used as switch. Yes, I've added a line over here. The purposes of this device is to provide higher current to the load. That means there is a need to operate load with higher current consumption. So the device actually need a higher current, and in order to control on and off this device to supply the power, power switching device, MOSFET, BJT, and diode are used. These components, they are not power supply. Students recap in the earlier portion that I mentioned that it is a switch. This is a switch. So a higher current will pass through this switch. Yeah. Another objective over here is that when the load device, when the load device need to be on and off at a higher frequency, then we will use these three devices over here. Yeah, I just want to explain this part because not all load device need to be switched on and off at a high frequency. Only certain device will need to do that. For example, lights that need to be dim, need to be brighter. So in that situations, we need to switch on and off the lights at different rates. For example, another example would be motor. So when the motor need to be driven at a higher frequency, we need to be able to send PWM signal, which is on and off at a high frequency. So these are the purpose of the component. Let's go into MOSFET. Right now, it's not new to us. MOSFET, we have learned MOSFET in your year one. I have actually put in your year one slide on the right hand side. They are pretty close. Yeah. So let me go through. There are three terminals, and each terminal has a name. Over here is a drain. Yeah, drain, whereby the drain current will flow through, and then there's a terminal called source. The drain terminal will pass through all the way down to the source. So eventually the load device that I mentioned earlier will be either connected here or connected here because they need the current, that is switched and controlled by this MOSFET. And then there's another terminal called the gate. The gate is actually a control pin. Yeah, the control pin will switch on and off this MOSFET. When the MOSFET is turned on and off, the load device is controlled accordingly. So let me jump to your lecture notes in year one. When you have gone through this part whereby over here, this one is the MOSFET that we were talking about earlier on, and then the control signal is over here. The drain current will actually pass through the drain terminal and then go down to the source terminal. So RD over here is our load device. It's either a fan or a light or a motor. So this one is RD. And in this situation, whereby there is a when there is no voltage applied at this point, and there's no voltage, 0 volt, it is equivalent to a open MOSFET. So the switch is open circuit, and because of that, ID will not be able to flow through, and because of that, the device, the load device, will not be supplied with any current. Students do take note that the power supply. Over here is VDD. So there is another power supply that is connected to VDD, either a battery or of some kind of a benchtop power supply. So this is what we call the cutoff region. Yeah, do get familiar with terms like that when we talk about cutoff, which means the gate of the Mosfet has a very low voltage that's insufficient to turn on the Mosfet itself. Yeah, so it's below the VGS threshold. Yeah, so because of that, ID will become 0, as I was explaining just now. Yeah, so just take note of this cutoff region, and now we will go on to the region whereby the switch is closed. Okay, over here the switch is closed, current is able to pass through ID, and then the load device will actually have current because the switch is closed. In order to do that, the voltage over here, V in, there's a condition. The V in condition has to be higher than the VGS TH. Yeah, one more time. VGS is similar to V in over here, because this V in will go through and then will send a signal to the gate. Yeah, this voltage over here, the VGS, need to be above a threshold. Yeah, when this happens, the MOSFET will close. This is our basics of MOSFET. So now at this point, the switch is fully turned on. It is called the ohmic region. Yeah, let us look into the characteristics, the I versus D characteristics. We often see this chart of a MOSFET. The y-axis is ID, yeah, ID, the drain current, and then on the x-axis is actually the VDS. Yeah, VDS is the voltage across drain source. Yeah, drain source. So the cutoff region is at this strip red. Yeah, the red strip area over here, they are the cutoff region. Why is that so? It's because at this region, we know that each line over here, each blue line is representing a different VGS. Yeah, a different VGS. So over here, the blue line represent a higher VGS, and at this point, the VGS is lower compared to this one. So at a level that is lower than the threshold, we mentioned this threshold, yeah, when it is lower than this threshold, it will go into this region whereby it is cut off. The MOSFET is cut off, or also operating at a switch off region. So what about the ohmic? The ohmic is in this region whereby you see these tinted green dotted lines. Yeah, from the green dotted lines to the left of these green dotted lines, this whole region here is called the ohmic region. This ohmic region is when we have quite high I drain. Yeah, I drain, we noted just now, is the current to the load. This drain current need to be high because it is intended to supply to the load device. Yeah, so it actually take on this stage, this side of the curve. The I drain is high, and at the same time, VDS, you can see that over at this green dotted to the left of the green dotted, the VDS is actually around this area. Yeah, I'm dotting this few area, the VDS. This VDS over here, they are at closer to 0 volt. Yeah, closer to 0 volt, because VDS is a voltage across the DNS, and DNS is actually the switch. Yeah, DNS is the switch. This whole thing is the switch. D and S is the voltage across the switch. So when the switch is closed in the ohmic region, we want D and S to be as small as possible. So that's why it is closer to the 0 volt. Yeah. So that when we are talking about V on over here, V on, it will be our VDS in the ohmic region. Sorry for my handwriting. Yeah, VDS is equal to your V on at the ohmic region. So whatever value that appears, it will be on the graph itself. Yes. And how about when we talk about the I leak over here, the I leak? How do we find out the I leak of the switch itself? Because this I leak is the current that go through the switch during the off state. So this one is the off state, and off state is also known in the Mosfet as a cutoff region. Yeah, cutoff region. So how do we find the I leak? Then we will need to go into the data sheet. If I page down to your notes that is used last year, you can see that this is one example that you have seen through in your notes. And the I leak of this MOSFET is indicated over here. Yeah, the I leak is known as the IDSS, zero gate voltage drain current. Yeah, is when the gate voltage is zero and the drain current over is indicated as 0.5 microamp. So I will indicate over here. This one is our IDSS. This point. Yeah. For the MOSFET, it is 0.5 microamp. How do I know that is IDSS? I will look into the data sheet, and on the data sheet itself, I check for off characteristics. Yeah, during cut off of the switch, I look into this parameter. It is called zero gate voltage. Zero gate voltage, it is a signal that go into the gate and that is below the threshold. Yeah, over here is indicated the GS is 0 volt, so the switch is off. With the switch off, this parameter IDSS is talking about the drain current. Yeah, drain current, and that is how we know that it is equal to 0.5 microamp. Yeah, it's a very small value of the I leakage. Okay, students, right now we want to go into the T on and T off. Yeah, T on and T off. How do I find my T on and T off of the switch? Since we are talking about MOSFET, so we already know that the MOSFET will require time for the voltage to change. Yeah, from here all the way down, it needs time, and for the current to ramp up, it actually needs time. T on. In the data sheet of the MOSFET, we can scroll down to the table below under the subtitle of switching characteristics. Over here, you can see T on, turn on time. Yeah, this is the same turn on time of this switch over here. Yeah, this same turn on time. So what is happening over here is that it actually takes 10 nanosecond. Okay, 10 nanosecond. There are actually two part number. These are the different part number BS170 and MMBF170. The difference between these two are, if you scroll up, there will be the different packaging. So the packaging over here is a DIP with the pin inserted into the through hole of the board. And over at this point, MMBF is actually referring to surface mount devices. There are no holes on the board because this pin will just sit on the board and being soldered. Yeah? So they are the same family, just different packaging. So going back to our T-on for this component is actually 10 nanoseconds. Students, nanoseconds 10 to the power of -9. So we are talking about this switch completing the turn on at 10 nanosecond. Yeah, for it to completely turn on. So in the same way, how do I find the T off? I will look into this particular T off over here. Yeah, turn off time. Turn off, this is a data sheet of a Mosfet. So when it talks about turn off here, which means the Mosfet is trying to switch itself off. Yeah, and the time that is required is the same, 10 nanosecond. So I would simply just indicate over here this portion as the same as 10 nanosecond. Yeah, this 10 nanosecond is the time that is required for the switch to switch off. You can see that the current slowly go down to a very small current, 0.5 microamp. Initially, it's at a high current that is required by the load, and then it's trying to switch off. The current will actually come down, will actually reduce, and it actually takes 10 nanosecond to complete the switching off. And students, let's take note also that the voltage here, the reason why the voltage rise during the switch off is because this voltage is referring to the voltage across the switch. Yeah, across the switch. It is not a voltage across the load. It is not across the load, but it's across the switch. So when the switch is open, no current flow, these 2 points, yeah, these 2 points will have a voltage that is close to E. That's why from low, a V on, go all the way up to a high voltage. Students, I just want to bring your attention to the notes in chapter 1. This one is the figure 1.8 that we were looking at, and figure 1.9 is the IV characteristics of a Mosfet. We talk about the two regions, ohmic and cutoff. And then at the bottom of it, I just want to bring your attention to these few sentences over here. Yeah, just now we spoke about IDSS. Yeah, it's a drain source current that contributes to I leakage during the off state. We have actually mentioned that. Yeah, I drain to source. And then we also have mentioned T on and T off. T on and T off are characteristics of the Mosfet that contributes, that contribute to the switching loss. Okay, students, on these power switching devices, this particular chapter, we are focusing on the switching loss. We talk about blocking loss, switching loss, and conduction loss. So for switching loss, the T on and the T off will actually affect the switching loss. The greater the T on and the T off, which means the component is taking a longer time to turn on and turn off, it will increase the switching loss. So that's how it works. Okay, the other thing that I want to bring your attention to is the current of the load device is determined by the Mosfet's drain current. Okay, what do I mean by that is this. The whole purpose of using a Mosfet is for me to control a load on top. Yeah, either I connect the load on top or I connect the load below to receive the drain current. The current, as I highlighted over here, the current of the load device is determined by the Mosfet. If let's say our load device require 1 ampere to work properly, okay, let me write this down. If the load current, okay, needs 1 amp, okay, if the load current needs 1 amp, for example, like this motor, let's give an example. If it needs 1 amp to operate properly, we need to find a Mosfet with ID bigger than 1 amp or close to 1 amp. Okay, because this MOSFET is a switch, it has to be able to take this 1 amp that the load needs. Okay, so that's how it works. MOSFET, I drain. If the MOSFET is chosen correctly, then the switch will be protected. This MOSFET will be protected. But if, let's say, we choose a switch in this case that is less than 1 amp, if we choose a MOSFET with ID less than 1 amp, this switch itself, this MOSFET switch, will be damaged. It will be damaged. Yeah, because the load current, when it is functioning, when the motor is functioning, it will draw 1 amp from the power supply because the device need 1 amp. But the current flow through the MOSFET itself could not withstand 1 amp because the rating, the specs is lesser than 1 amp, the MOSFET switch will be damaged. Let us go into the datasheet to look for this drain current. Okay, this is the MOSFET that we have seen. The drain current usually is stated at a few places. One place is over here at the description. Yeah, says over here they can be used in most applications requiring up to 500 milliampere DC. Yeah, so this one is referring to drain current. This description might be unclear. To talk about drain current, if we scroll down to the table will tell us clearly. The drain current, continuous means my motor will always be running. Yeah, always be running. Continuous drain current, because this is my load current. It is 500 milliamp. Yeah, 500 milliamp. So that is how we make sure that the MOSFET is chosen correctly. And this is what I have indicated in the notes over here. Sorry, students, I'm switching different documents to help us see the whole picture. The current of the load device is determined. Yeah, we need to set the MOSFET correctly. Yeah, because the MOSFET ID, the drain current, will actually be limiting the load device and be damaged. Okay,